sharing the slides. Three electrode system, right?
Okay.
Just share. Then which one you don't understand? Which one?
The working function of electrode.
You can see the slide, right?
Okay. Three electrode, sir.
Three electrode. This one, right?
Yes, sir.
Okay. So it is visible. Okay. See.
Okay.
So three electrode systems. I mean, so why we need three electrode system, right? For in the biosensor. This one. See. So generally, we are using generally the two electrode system. Generally in the battery like this. I mean, there is two electrode like cathode and anode, right? One is cathode and another is the anode. One is the positive electrode and another is the negative electrode, right? Generally in the battery case. But in the three electrode system, we need three. Why three? Because we want to fix the potential, or we want to measure the current or charge on that is on working electrode, right? So suppose this one is the working electrode. Okay, your name is Sumon, right? What is your name? Hello.
Suman, sir. Suman, sir.
Sumon. Okay. See, so suppose this is the working electrode. So this working electrode on this working electrode will apply certain potential E, certain potential. Suppose 0.3 volt. So with respect to which we are applying 0.3 volt. So some potential on the same solution should be fixed, right? So this is the reference electrode here. So reference electrode potential will be we are applying some potential with respect to this electrode. So this is our reference. Means some potential we already know before, right? So we already know the potential of this reference electrode. So we are applying suppose 0.3 volt. So that is respect to reference electrode. So it is kind of the potential will be always constant. With respect to this, we are applying some potential on working electrode, and then when some potential will apply on the working electrode, then in this solution, some chemical will be there, right? Or maybe from the surface, from the working electrode surface, we are immobilizing nanomaterials and biological stuff, everything, right? So there is some electron transfer between solution and the electrode surface. So that electron will be we can measure by the help of counter electrode. Number 3 electrode is the counter electrode. Okay, so that electron can transfer through the counter electrode, or we can measure the current or charge. So we'll get one output. We have some signal output. There we can see like cyclic voltammogram or chronoamperometry like this, or chronocoulometry like this. You can see, right? So that will help actually. That electron will flow through the counter electrode. So counter electrode will help to measure that electron. So basically, in the three electron system, one is the working, where we'll work to modify the biosensor on the surface. Another is the reference on which we are actually applying some potential with respect to this. This is the standard or some fixed potential will be there. That potential will be well known. And third one is the counter electrode. So by which we will measure the now how many electron flowing through the working electrode surface. So that number of the electron will be measured through counter electrode. Yeah. So it's
Hello, sir.
these three electrodes should be dipped in a solution always, not the solid. So it should be in a solution. Yeah, tell me.
Sir, AB means what? Charge or current?
Which one? Which one?
AB, sir, is directed in arrow.
AB in the here. This one. Your voice not clear, Suman.
AB, sir, AB. Yes,
Oh,
AB.
AB. Yeah, yeah. AB means see here. That is the see. This is the current directions. AB means similar like this here. Means which direction? I mean, sometime electron can be. I mean that the oxidation reaction sometimes happen, right? Sometimes electron maybe from solution to the surface, maybe electron will flow from the sometimes some surface to solution, electron will flow. So AB means that direction. Sometime this way, sometime that way. Hmm. Sometime from potentiostat to the solution, or sometimes solution to the potentiostat. That will be measured. Hmm. Okay.
Okay, sir. Okay.
Sir, sir,
Yeah.
I have a question, sir. Sir,
Yeah.
like working sir,
Yeah.
hello.
Tell me. Who? Beauty. Yeah. Tell me.
Yes, sir. Sir, the slide is not visible. Okay, sir. So the working electrode, on the working electrode, we immobilize the our biosensor, and the
Mhm.
counter electrode is for the completing the circuit for the transfer of the electrons.
Transfer of the
And
electron.
sir, yes, sir. But the what is the role of the reference electrode? Means I mean to say, with the help of the potential state, we are giving some potential between the reference and the working electrode,
Yeah.
right, sir?
Right. Right.
So
You're right.
we already know the potential that we are applying between these two electrodes. So
Hmm.
how the reference electrode will be the helpful to know this potential between these two electrodes, sir? So
See,
we
suppose
already know the potential that we'll be using through the potential state, sir.
see through the potentiostat, there is a program file. There you will get some chart. So like input, how much current you are applying, which sorry, how much potential you are applying, initial, final, like in the cyclic voltammogram, right? So some cyclic voltammogram, you are starting potential this one, final potential this one. You can fix that one in the potentiostat that you can apply. So that potential will be applied through the reference. I mean, through the working electrode and reference electrode. That potential difference will be measured. So when we'll apply some potential through the potentiostat, okay, so that actually will go through this reference electrode. If it is silver chloride, see if it is silver chloride, see, okay, just see here. Although you are applying through the instrument, if it is like, see, it is like minus 0.3, and here suppose 0.5 plus. So if it is silver chloride, maybe you will get something like this by cyclic diagram. Okay, minus 0.3 to 0.5. But if it is hydrogen reference electrode, then so this one will be start from here, not from, because hydrogen reference electrode case, uh, so it is around my 0.1 volt. I mean hydrogen is plus, plus, I mean 0, it is, we are considering hydrogen 0, and AgCl we are considering plus 0.1 volt, right? So that's why if AgCl case you are getting from minus 0.3, then from the hydrogen electrode case you will not, it will not start from here. Okay, it will not start from here. So it will start from where? Can you tell me where it, from where it will start from the hydrogen electrode?
It will start from zero.
Uh, yeah. So no. See, if so, the difference between AgCl and hydrogen electrode and AgCl difference, suppose 0.1 volt plus 0.1 volt, right? So if AgCl start from minus 0.3, then it will start from negative side of, from here in zero point 0.1 volt, left side it will start. From hydrogen case it will start from here, right? So this will decide the reference electrode from where it will start, because this reference electrode potential is constant. So you are applying some potential through the potentiostat, and all it can be recognized by the reference electrode. So if it is AgS is a reference electrode, then it will start from here. If it is hydrogen electrode, then in case it will start from here. Hmm. Okay.
Okay, sir.
So that one actually will be considered by the reference electrode. So although you are applying potential through the potentiostat, but in the output, so starting point, end point, that will fully depend on which reference electrode you are using. Hmm. So in the same solution, same potential, so, like you are using like APCl3, some solution, right? So if I use silver chloride, then it will start from here. No, sorry, I mean right hand side, that one. If it is hydrogen electrode, then it will start from here, the same solution, but the starting point will be the different if you change the reference electrode. Clear now?
Yes, sir.
Okay. Any other questions? Okay, then go to the new topic.
Sir, excuse me, sir.
Yeah, tell me.
Sir, in cyclic voltammetry, hello.
Yeah.
Sir, can we start from the reduction part itself, and then when can we do oxidation one?
That's good questions. Nice. I'm explaining your question. See, so yesterday, that day I told that we can start from Fe2 plus to Fe3 plus. That is oxidation, right? So for the oxidation, we have to start from left hand side because you have the Fe2 plus. But if you have Fe3 plus already in your solution, then you have to start from right hand side, from reduction first. It will start from here. First reduction it will happen, then oxidation. Okay, so plus to minus. Then you have to scan from right hand side first, then left hand side. Clear? So if you have the already, if it is oxidized, so you have to use like ferric chloride. So it is already oxidized class 3 stage. But for this CB, maybe you have to use ferrous chloride, Fe2, FeCl2, mean plus 2 oxidation state. So it will transfer to Fe3 plus. But in this case, you have to start from Fe3 plus, means it will be reduced to Fe2 plus. Clear?
Yes, sir.
Clear?
Yes, sir. If initial material is Fe3 plus, then there will be a reduction curve first.
First reduction. You have to reduce it first. Right? So it is kind of now kind of like your general idea or common sense you have to use. So when you will get all the knowledge, then you can use your common sense. Like, yeah, I have the higher oxidation state. Let's reduce it first. Then we will go the lower oxidation state. Right?
Sir, we need to know the oxidation state of the solution, right? First, then
Yeah,
only we can do.
Definitely. Which one you are using? That one you have to know which solution you are using.
Okay, sir. Yeah.
Clear? Good question. Any other questions from your
Sir?
side?
Yeah. Hello,
Sir?
sir.
Yeah, tell me. Please ask one by one. Please ask. Who is asking?
Sir,
Yeah, yeah.
Vibhuti here.
Yeah,
Sir,
ask me.
is there any criteria for the the reversible reactions? So, what will be the criteria for the reversible reactions, sir?
Criteria for reversible reaction, I don't understand. Can you please repeat your question?
Sir, like one substance will be oxidized, and if it's can be reducible, then it will reducible. So, is there any criteria for both the reactions to be happen?
No, as I said last time, you are using some solution in the biosensor. Suppose you have the glucose solution, right? Okay, so like you
Yes.
want to measure the glucose concentration in your biosensor. You want to measure the glucose concentration. So in this case, in the solution, you have to take the glucose, right? Now you know that glucose actually means slowly you will understand. Glucose means you have to know that it is actually you can say some substrate that can be oxidized only. So we cannot reduce it. So means uh, generally we are oxidizing the glucose. So then it will form the gluconic acid, higher oxidation state. So think about glucose is the lower oxidation state generally. So in this case, if you oxidize it, then it will show you some peak, but there is no reduction peak because it is not a redox. There is no redox couple here. It is some kind of substrate that is not like iron redox couple. It is some kind of substrate that can be only oxidized, but it will not be reduced. So there is no reduction peak, so you will see the very good oxidation peak. Then if you increase the oxidation of glucose, then you will see higher like this, then higher peak, then higher peak. The peak will be increase and increase if you increase the concentration of glucose. So from the current level, you can understand the concentration of the glucose. That I will teach you how you will measure the concentration of the glucose. That I will teach you today. Okay, Vibhuti. Another thing, so for like if it is the redox, some redox couple like iron or like something like ruthenium, ruthenium 2 and ruthenium 3 possible, right? Ruthenium chloride or ruthenium hexaamine, some complex available. There are 2 and 3 oxidation states like this. So any compound, if it is a redox couple present already, there in that time you will get something like this CV, a very good oxidation peak and reduction peak, and they will be very close to each other. If it is very close to each other, means they are very reversible reaction. Because of this, you are getting very close. If the redox couple, but you are getting this oxidation and reduction peak very far to each other, I mean, it can be like this, like 1 CV maybe. Oh, sorry. So 1 CV maybe something like this. We here oxidation, then here maybe reduction. So oxidation peak you are getting here, reduction peak you are getting here. So if this oxidation reduction peak is very far from to each other, so it means the electron transfer, this uh, means that higher to lower, that conversion is very low, not very fast. Means it is irreversible. Irreversible. Then in this case, these two peaks will be far from each other. Okay, Vibhuti?
Yes, sir. Got it, sir.
Okay. Any other questions?
Yes, sir. Hello, sir. Sir, hello.
Who? Tell me,
Sir.
Suman. Suman, right?
Yes, sir. Yes, sir.
Tell me.
Sir, in cyclic protometry, please share the slide. Sir, IPA and IPC are equal.
IPA and IPC
are equal.
Equal means no. IP means the see, P means potent. This is the anodic. PA means peak or anodic. Okay, so this is EPA means this potential. Okay, just see. So in this, so this is the potential axis, x-axis, right? So this potential is the anodic peak potential, and corresponding current. Corresponding current means this y-axis, right? This is IPA, and in this case, IPC means cathodic current, means highest current you are getting in that potential, that is cathodic peak potential, and this corresponding current is the cathodic peak current. So this is IPC, this one.
Sir, okay. I say in magnitude, say only.
Oh, magnitude, it can be same, it cannot be same. So in this compound, it looks like similar. But magnitude sometimes may not be same. That depends on this vary to compound to compound. Good.
Oh, okay, sir. Sir, last question, sir. Sir, what is background current? Please, once more time.
See, background means, see here. So you can see, although it is 0, this is the 0, right? But it is not starting from the 0, right? At the background, you are getting little bit current at the beginning. So this one, if you think about, if you consider a straight line from here to here, and from here also, so this is the background, actual background current you are getting. I will clarify by drawing a picture. See, suppose so your CV actually starting from here, right? So it should start from 0, but it is not starting from 0. So this much current you are getting at the beginning. Clear? So this much current. So if you, and this is the reduction, and suppose it is stop here. So if you dot like this, and from reduction also if you dot like this, so this is actually, it is called a kind of capacitive current or background current. So capacitive current, this one I will let you know later. Just think about, this is the background, some current you are getting at the beginning. So that is the background.
Sir, it is must be applied or not produced. Sir?
This one must be
produced or applied, sir. background current?
No, background current is not applied. It will be produced. It is depend on your which potential you are applying, which compound you are applying, which solution you are using. So depend on that. So you will get some background current.
Or magnitude is very small, na?
Magnitude is very small, but it is
Okay.
showing. Yeah, sometimes maybe if your concentration is very high, maybe it will be the higher current. You will get the higher.
Okay, sir. Okay, sir. I got it.
Okay, good. Yeah, keep asking. I think someone raise your hand. Who? Bhavesh. Bhavesh Dalta. Datla.
Yes, sir. So, like during immobilization,
Huh?
so we are doing a washing. So, sir, is there any specific solution or something we should use for the washing, or it's not means required for that?
Yeah, for washing, actually, we are using some washing buffer. We are saying that it is buffer solution. Washing buffer. So washing buffer is content is PBS plus BSA. That actually I am going to teach you, but as you asked me, I am going to say. So washing is going to, it is kind of the different kind of buffer. So PBS means phosphate buffer saline. PBS, phosphate buffer saline. So generally its pH is around 7.4 pH. So it is close to our blood pH. So what is PBS? PBS, it is actually phosphate sodium phosphate, Na3PH4, and Na2 Na3PH4 and Na2H H2PO4, something like this, right? Sodium, one is sodium hydrogen phosphate, and another is sodium phosphate. Right. So sodium hydrogen phosphate will be Na2HPO4. Okay. Okay. So these two solutions salt mixture. So this is kind of why I am saying it is buffer solution, because its pH of this solution will not be changed if little bit amount acid or base if we add in this solution, the pH will be almost constant. So sometime during our experiment, maybe when we are adding some chemical, the pH can be changed because of addition from the outside reagent. But this buffer actually will help you to keep constant the pH. So buffer means the pH will be constant. If foreign from outside, if you want to add some chemical or something like this, they will not change your whole pH of the solution. That is the buffer solution. So PBS is the sodium phosphate and sodium hydrogen phosphate mixture, and BSA. BSA is the biovin serum albumin. This is one protein. So why we are adding BSA? Actually, this kind of protein actually will help you for non-specific binding. So that actually I'm going to teach you. You don't know the non-specific binding term. So I will tell you first. Then you will understand why I am using BSA. That time I will teach you why I am using BSA. Okay.
Okay, sir, like my doubt, like uh, our washing solution should always be dependent on the particle we are trying to immobilize, or it's general for every time.
Definitely, sometime we need some different washing solution that depend on which one you are immobilizing on the surface. But in general, this is actually you can make the universal some buffer washing buffer like PBS plus BSA. This solution you can I mean use as a universal buffer solution. Okay, but you can change this component pH and some other component also you can add, so that I will tell you.
Okay,
Okay.
thank you, sir.
Okay, any other questions? So every Wednesday maybe we can have out this kind of the discussion, so maybe you can ask the questions, I can clarify you also. So maybe after class also we can start this one. Let's start some new topic. Okay, then we can ask you again questions and you can ask me the question. Okay, so until last class I taught you the cyclic voltammetry. So cyclic voltammetry is kind of it is kind of the cyclic scan, like we are from the left hand the negative scan and right hand is the positive scan. So we are starting from negative to positive, then positive to negative. So uh, negative to positive means it is the oxidation scan, means it will start the oxidation, and positive to negative means reduction scan. So it will start from I mean higher oxidation state to lower oxidation state. Oxidation means lower oxidation state to higher oxidation state. So cyclic voltammetry will give you some information, like if it is the two peak, it means there is some reversible reaction, oxidation reduction. If you are getting only one peak, no reduction peak, it means there is highly irreversible reaction, you are getting only oxidation. So many information you will get. Also you will get some information where the oxidation happened, where the reduction happened. So if you want to develop some oxidation based biosensor, then you can understand how much potential you need to apply. So this kind of information you will get from cyclic voltammetry. And chronoamperometry kind of the this is the electrochemical technique where you will apply some constant potential, and you will get like that is current versus time curve. So with respect to like something like 5 minutes, 6 minutes, or something like so how long you are running your experiment, and within at the beginning, at the very starting point, you will get the higher current. Then slowly it will be stabilized, and you will get almost constant current. So you will measure the current. You will when this current will be constant. So you have to choose that time. So any time you can choose, maybe around 4 or 5, 6, 7, because the current is become almost constant. Then you will get certain value. I mean, at that applied potential. So how much current you are getting, that you can make, right? So this is actually information we are getting from chronoamperometry. We are getting how much current we are getting from the biosensor. And chronocoulometry case, we are applying some certain potential here also same, but in this case we are getting charge with respect to time. So you can see, so if we like increase, if we, in a like oxidation case, so if you increase the oxidation potential, maybe here you are getting like 0.1 volt, here like 0.2 volt, here 0.3 volt, 0.4 volt. So suppose like this, if you increase the like your applied potential, slowly you will get the higher and higher charge with respect to time. That is the for chronocoulomb. So this is the chronocoulomb, and technique is called chronocoulometry. Okay, so that is until in last class. So today I will teach you some biosensor where we will modify the surface and we will apply those three techniques: cyclic voltammetry, chronocoulometry, and chronoamperometry. We will apply them. So how we will get the information from the biosensor? So yesterday, last class we learned. Now we are applying those three techniques. See, so this is the transducer. This is the transducer. Suppose on electrode surface, where we are immobilizing first avidin. So as I told you, avidin is a kind of protein. So where biotinylated antibody. So this is called antibody 1. That is the primary antibody. This black one is the biotin. So as it is biotin conjugated, so we can easily immobilize on the solution. Easily immobilize on the surface, on the avidin modified surface. Right, guys? It is very easy, right? Common process. So if your surface already avidin coated, then you can easily modify your primary antibody that is already conjugated with biotin, right? So it is your biosensor surface is ready for the detection. Clear? Now you are dropping a blood, suppose a sample, like blood sample. So here your sample is ready to drop. So please, guys, you mute yourself who are not asking me question or anything. Because there is lots of background. Who are not talking, please mute. So if you want to ask any question, then only you unmute, then we can start interaction. See, so your surface transducer already avidin coated. Now you are immobilizing antibody that is biotin modified, already immobilized. Then you can modify. This is your sensor ready. Now you are dropping a 1 drop blood sample. So this blood sample contain your target. Target means your biomarker. So biomarker means so that the protein you want to detect. So like this target. So one target may be your maybe cancer, some dengue, malaria. So any kind of target you want to detect from blood sample. So that target will be bind. Why it will be bind? Why it will be bind? Because this target and this antibody, primary antibody, they are very, very specific. So this is called antigen antibody interaction. So antigen antibody, they have interaction. This is the actual natural interaction they have. So this is specific. So you have to immobilize those antibodies. That antibodies should be very, very specific with the target. So it should not interact with any other one. So if you want to detect the like cancer, like suppose prostate specific antigen, prostate cancer related antigen you want to detect, then you have to immobilize only that antibody. Okay. Now after dropping your sample, if you have target, it will be fine. Then you have to wash it. You have to wash it. So washing is necessary. Why? Because if there is any unbound one, so that should be removed. That should be removed from the surface. Unbound one. So why we should be removed? Because next step when we will add some secondary antibody. So if some antigen or target somehow, wait, I just clean it. So if some target is not maybe here, maybe some target maybe there. When you're dropping the blood can be spread here also, right? So some target also there. So if you not remove by washing from here, then secondary antibody, it can bind also here also, right? So that secondary antibody can actually cause some background current. That's why you should remove. That is free. That is not on the surface on your antibody coated surface. That should be removed. Now you are adding the secondary antibody, that is nanoparticle conjugated, right? So that secondary antibody will bind on the target. Now you have to wash it again. So you need again one more step washing. So why we need second step washing? Because when you add some secondary antibody, again that secondary antibody also can be here, gold can be here. So if there is no no target, if there is no target, a secondary antibody cannot bind, so they will be removed from the surface. But if there is target, then secondary antibody will be bind on the surface. And while washing, because of the strong interaction, they will not remove, they will be on the surface. So basically you are getting a biosensor surface that is primary antibody, target, and secondary. This kind of sandwich formation you are getting on the biosensor surface. Okay, I'm going to repeat it again. Just make it clear again. So this is full biosensor. Then we will apply our electrochemical cyclic voltammetry, chronoamperometry, and chronocoulometry technique here. And how we'll detect the different concentration target. See, again, let's go back. So this is your transducer surface, right? So here you have to modify first one linker like Avidin. So that will help you to immobilize your primary antibody. Now you are going to draw your sample like blood, or it can be saliva, serum, urine. So if that sample contains some target, this target will bind on your surface. Now you have to wash it because that is not bind on the surface, it should be removed. Then you are adding the secondary antibody conjugated, that is gold conjugated antibody. So, and you have to wash it again. Then, so if there is so many unbound one, so they will be removed from other place. They will be removed. So you are getting only the biosensor surface, that is target. If there is target, then only you are getting some gold nanoparticle on the surface. Otherwise, you will not get any gold nanoparticle. Suppose, let's go back. So if your sample does not have any target, patient is healthy, no cancer, patient is healthy. So you will not get any target here. The target will be absent. Okay. So this will be absent. So in this case, like this target, this will be absent. So this is cross, no. Then when you are adding secondary antibody, as there is no target, see this target, no. That's why this secondary antibody cannot bind on the surface because of antigen antibody interaction. That's why secondary antibody bound. And because secondary antibody already conjugated gold nanoparticle, that's why you are getting gold nanoparticle on the surface. So if there is if there is no target, so basically you are not getting any gold nanoparticle on the surface. Clear? So if there is no gold nanoparticle on the surface, then actually you will not have any kind of the reaction. Means basically we are using, can you remember last time I taught you like nitrophenol, it is converted to the aminophenol, I taught you, right? So this conversion only possible. So nitrophenol here the chemical or substrate. Aminophenol is the product, right? So if there is no gold nanoparticle, you are not getting any aminophenol. Clear, students? Is it clear?
Yes, sir.
So
Yes, sir.
so that's why. So you are getting, if there, see, I showed only one antibody. Actually, so you in the surface you will have many thousands antibody will be there on the surface. So if your target concentration is very high in the blood sample, so you will get the many target, right? So many target means many secondary antibody that conjugated with gold, right? So many gold means this reaction means formation of aminophenol will be very, very high. Means so many so many nitrophenol, NP, will be converted to so many aminophenol. So basically you are getting so many product, this AP on the surface. Okay, so more AP means, see here, now this product P, so AP, this P. So this P will be oxidized on the surface. So when we are applying some potential, so we are going to apply some potential, right? On the chronocoulometry or chronoamperometry, suppose 0.3 volt, we will apply. So on that potential, this product, I mean here AP, will be oxidized and will get some electron. So this electron will flow through your counter electrode, right? And you will get in the form of current or in the form of charge. So now, if you have more gold, means more aminophenol will be oxidized on the surface. So you will get the more and more electron on the surface. So more and more electron means your current will be the much higher. So if your sample contain more, high concentration target, then you will basically get the high amount of current or charge. Clear? Students, is it clear? Why? Yeah. Okay, learn now. Let's show
Sir.
you.
Sir,
Yeah, tell me.
sir, like in a normal biosensor device, like to detect any kind of disease or any kind of thing. So, sir, there's no way to wash the biosensor. So, how we are going to do this? Like if there's a glucometer,
See,
it will not
in
wash.
the glucometer in this case, generally we can develop two kind of biosensor. So right now I am teaching you washing is necessary. So then I will teach you wash-free biosensor. Some biosensor we can make it wash-free. Okay, so that I will teach you, but not now. Maybe after few classes, because at first you have to understand the basic things. Then I will go to advanced. Okay. Clear?
Okay,
So for the wash-free, we can make some chip actually. So on the chip, we can make some channel. So on the channel, we can make the wash-free. That I will teach you later. First, understand the basic one. Okay. That part I will come. Okay. So this is the washing related bias. So we need to wash it. Now, this biosensor will apply the electrochemical technique. So which I will apply. A means CV means cyclic voltammetry, CA chronoamperometry, CC chronocoulometry. This technique I will apply. See, so this is the cyclic voltammetry. See, so we are getting, so if it is gold nanoparticle present, then you are getting product, that is aminophenol, right? So this aminophenol can be oxidized. So if you run cyclic voltammetry in this solution, So you can, in a beaker, you can, so there should be some like buffer solution, PBS, that will be contain some nitrophenol. Okay, so now your working electrode, this one, or your working electrode, right? This is your working electrode. So if in the working electrode surface, this sandwich will be formed, this sandwich. So this sandwich on your working electrode surface. Now, as your working electrode surface already contain gold nanoparticle, so this NP will be converted to AP, and this AP will be in the solution, AP, right? Now, so there will be a reference electrode and counter electrode, reference and counter. Now, if when you are applying cyclic voltammetry, suppose 0 to 0.5 volt, right? You are applying. So in this potential, so AP will be oxidized. At first, it will be oxidized. Then again, when you will back scan, means it will be reduced. You will get something like this CV in the aminophenol. So aminophenol also, do you know the structure of the aminophenol? So it is something like this: amine group and OH group. And it is when it will be oxidized, it will form something like this, quinone, something like this. So actually, this is the reversible reaction. So aminophenol quinone formation, it is a reversible reaction. So that's why you will get a very good oxidation peak and reduction peak. Okay. Now how you will measure the different concentration target? So if you increase the target concentration, then more gold nanoparticle will form, more aminophenol will form. You are getting higher electron. So that's why. So your CV current also will be increased because of higher amount of the electron. Your peak current, that also will be increased, something like this. Okay, so again, for example, this blue one for the zero concentration. So why at the zero concentration, so you will get some this kind of the CV, because of the some very small background current you will have, very small background current you will have. That's why you will get one CV, but that is also small current. But when you increase the target, like from 1 nanogram per ml, this is the unit, nanogram per ml, then you can increase 10 nanogram per ml target concentration, then 100 nanogram per ml. So this kind of concentration, if you increase, so if you increase, so 1 nano, maybe you will get like this. Then if you increase 10 nanogram per ml, then you will get higher current. Now, if we increase like 100 nano, then 1 microgram per ml, then again you will get the higher, like this. Okay, clear? So like this way, your current will be increased when you increase the target concentration. Clear, guys? So from the cyclic voltammetry, like this way, you can predict how much concentration of target present. So for that, we need a calibration curve now. That calibration curve I will teach you now. So what is the calibration? See. So now you have to make a plot. What? The calibration plot. So here, as I told you, so you get the zero concentration, then 1 nano, 10 nano, 100 nano, 1 micro, like this. So you increase the concentration of the target. That's why you're getting higher and higher. So let's plot. So in the x-axis, you have to plot the concentration of target. Okay. In y-axis, you have to plot current. Current means how much current you are getting from the cyclic voltammetry or any kind of technique. So as I said, in the zero case, suppose you will get some current, although not zero, you will get some current for the zero concentration of target. What is the zero concentration of target? Because if there is if your sample does not contain any cancer marker, then your secondary antibody will not bind, right? So if this antibody not bind, then no gold nanoparticle, then no nitrophenol will be converted to aminophenol. But still, because of the nitrophenol, you will get very small current. Why very small? Because it is not that much electroactive. Aminophenol is very electroactive. That's why you will get very, very high number of the electron. So so we that is not the ideal compound. When we will apply some oxidation potential, it is not ideal that you will not transfer any electron. You will transfer some electron. So that's why you will get some electron current in the zero concentration also. That is called your background current. That is called your background. So background current of a biosensor. So what is the definition of a background current of a biosensor? So if you do not have any target in your sample, but still you will get some current. Why you will get some current? Because you are using some substrate. So that substrate you have to use always, right? In zero case also, target case also, every time you have to use the substrate. Because of substrate, we will get some current. That current amount is called background current. Clear, guys? Hello, students.
Okay.
Is it clear?
Yes,
What is
sir. Clear.
background
Yes, sir.
current? Okay, so this is your background current. Now see. So if you're increasing the target concentration, suppose 1 nano. So this is your zero current. This is your 1 nano current, right? So 1 nano current you can plot here. Then 10 nano here, right? So you can plot 10 nano like this way, 100 nano, 1 micro. So you can increase the concentration like 0. So this is 0, this much current. So this is 1 nano concentration, you are getting this much current. 10 nano, you are getting this one. So like this way. So x-axis is the concentration, y-axis is the current. Corresponding current and concentration that plot you are getting. This is the calibration plot of this biosensor. Suppose I am providing you a unknown sample. Now come to the practical application. So I am giving you a tube, sample tube that contains some cancer sample. You don't know which concentration of this prostate cancer present in this sample. So how you will calculate? So you already made this calibration plot by using different concentration of cancer marker. So you know you will have in your hand this calibration curve. Now with the unknown sample, suppose you are getting this CV. So you have to run CV, you are getting this CV. So how much current you are getting in this peak potential? How much current you are getting in this case? Suppose this much, right? Suppose it is you are getting 5 milliampere current you are getting in the unknown sample. So this 5 milliampere, let's compare with your calibration plot. So this is y-axis is the current, right? So suppose it is here 5 milliampere. So you have to make a straight line, just straight line with this calibration plot here. Then go again one vertical straight line in the concentration x-axis. So 5 milliampere corresponds to this much concentration of your biomarker, like PSA, post-processing antigen, right? So now you can say your unknown sample contain this much concentration of prostate-specific antigen. Clear?
Sir, I have one question.
Yeah, tell me.
Sir, I didn't understand that in the starting you were preparing some this starting first. I have one question that what is the relationship between the current and the concentration? I mean, this plot is first we are drawing the plot and then identifying some unknown sample.
Hmm.
I don't understand that current and concentration. I mean, this plot should be either straight line, or how we will know that this is only this type of straight line or some other type of the curve.
Yeah, so this is actually very ideal case. Generally we are getting this straight line, but sometimes non-ideal case, sometimes it can be here, it can be here some plot, right? Or it can be like sigma type, like sigma, like this type also. So it can be like this type also. It's possible. Okay, so in this case, okay, so let's remove this one. It is also nice questions, Vibhuti, right? So in this case also you can plot like this way. So that I am teaching you, that is very ideal case. Non-ideal case, suppose, so this is concentration and this is current. So 0 case you are getting here. Suppose 1 nano case you are getting here, 10 nano case here, then 100 nano maybe you are getting here, right? Then 1 micro here, 10 micro here. So it can be like this. Okay, right? Right, Vyuti?
Yes, sir. Yes.
Sir,
Okay. Just a minute. Just a minute. I just make it clear this question. Just a minute. 1 minute.
Yes.
So it can be like this, right? So
Okay.
one thing you can do, you can make a straight line by using the maximum dot. So that is correlation. Maybe you know the correlation coefficient, so that it could be 0.99 or 0.97, something like this. So that correlation coefficient, by using this, you can make the maximum dot in your line. If it is not like this, so you have to make like this curve only. Then similar way, you just draw a line by using all the like this way. You can make it like this kind of like S curve, like sigmoid. Then similar way, get current, then you will get the concentration. So get the current, then you will get your unknown concentration. Get the current, the unknown concentration. Okay.
Yes, sir.
Okay. Tell me other questions. So someone you're going to ask me.
not sir. I actually said that the curve is nature depend on material nature actually, and concentration material nature.
Yeah,
Ideal.
nice. Okay.
Yes.
That actually will depend on your biosensor nature. Yeah, what kind of biosensor you are going to develop. So sometimes you are getting straight line, sometimes you are getting sigmoid type. It's depend on your biosensor. Every time you will not get similar shape. Different shape you will get.
Okay, sir. Okay. Sir.
Nice. You are asking, everyone asking very good questions. You can keep asking. See now, see here, as I said here. So once this is kind of the CV. You can see. So this is suppose for glucose. So glucose case, maybe we will not get any reduction peak, right? So you are getting oxidation. So you have to first make constant one potential. So suppose in this potential you are getting highest current, right? For the background case. So this blue one is the background, right? So you are getting one peak here. So you are getting highest current. So fix this potential. On that potential, you have to get all the current for other concentration also, right? So this is the technique. You have to fix a potential. On that potential, you have to get all the current for all the concentration. And then you have to plot the calibration curve. Okay, now see the chronoamperometry. So this is the CA. So similar way. So here, as I said, in this biosensor, so you will get the chronoamperometry also. See, so suppose this is the 0 concentration, then 1 nanogram, so 1 nanogram per ml, 10 nanogram per ml, 100 nanogram per ml, 1 microgram per ml. So like this way. So if you increase the concentration, basically you will get higher and higher current. So your chronoamperometry will be like this. So this is some kind of practical curve we got in our lab. That actually I'm showing in this slide. So sometimes they can be merged, sometimes. So it is very difficult. Maybe means ideal chronoamperometry, it is like this. Suppose it is 1 nanogram per ml. So suppose 10 nanogram per ml. So this is ideal, like 100 nanogram per ml. Then 1 microgram per ml. So you can very clear difference. But sometimes they can be merged to each other. So in this case, what you have to do, you have to choose a time. Suppose think about 30 seconds. So in this 30 seconds, see they are all are separated to each other, right? So in this time, you have to measure all the current to get the calibration curve. But if you choose, suppose here 45 seconds, see they are merged to each other. So you will not get any difference between these two concentrations. So you have to choose one time where all the curves are very well separated. So you get all the current difference, and you can make the then here concentration versus current. Then different concentration, then different concentration, different current you will get. Then you will get the calibration curve from the CA. So in the case of CA, you have to fix a time where all are very well separated current. And in the cyclic voltammetry, you have to fix a potential. On that potential, you will get very well separated current difference. You have to fix a potential. Yeah. Clear, guys? Students.
This time selection, how we will know that in this time range or at this point of time we will get separated curve for
That
Coulomb
that
spirometry?
that you will get from your data. So you have to get the data set. Okay. So when you everything, your biosensor formation, everything done, then you have to go for your data set. Then you have to overlay all the concentration within one chart. This is called concentration chart. So in this chart, you have to plot all the concentration curve. Then you can see this difference where. Then you have to fix this one. So this depends from sometimes it's different to biosensor to biosensor. So in this biosensor, 30 seconds they are well separated. So some biosensors case maybe 40 seconds is well separated. So you have to decide it from the chart. Clear? Hello?
Yes, sir, clear.
Okay, sir.
Good. Okay. So this is for amperometry. Okay, now let's come the chronocoulometry. So how it looks like for the chronocoulometry case. Can you tell me this one? See. So this is the chronocoulometry. As I told you, I taught you already. Chronocoulometry, charge versus time, and chronocoulometry case, it is very easy because they always will be increase and increase. They will not be saturated because, as I said, the charge equals to current into time. So as time always increase, and although your current saturated, but because of multiplying with time, so it will be increase always. See, so suppose, see here in the zero case you are getting this much. So here we measure until 200 second, 0 to 200 second. So you can consider 200 second because here you can see the very big difference. But you can measure still, but it is enough. In the biosensor, you can measure until 60 second is the standard time, and you have to measure at least 1 minute, or you can measure more. So generally it is recommended let's measure more than 60. As so I measured here until 200 second. So at the 200 second you can get all the charge for all the concentration. So zero case you are getting this much millicoulomb. Charge unit is coulomb, right? MC means millicoulomb. So zero case you are getting this much charge. So this is the picogram per ml. This is a very, very low concentration unit. So I think you know already, right? I can show you. Nano means, nanogram per ml. Nano means 10 to the power minus 9, right? On nano, and then you can go more pico. So this is 1 nano. 1 nano equals to this 1 picogram per ml. 1 pico means 10 to the power. Then you can go more 10, right? 10 to the power minus how much? Minus 12, right? Minus 12, yeah. And then another is femtogram per ml. 1 femto equals to 10 to the power minus 15. So this much very, very low concentration unit. So you can see the FG now. So first image, so this is, see, femto is the lower concentration. And then you can go to micro. Micro is a 10 to the power minus 6. So 1 microgram per ml. So micro is the higher concentration, you can say highest in this case. Nano is the intermediate, and pico is the also then lower than nano, and lowest concentration is the femto, Fg, femtogram. Lowest concentration is very, very low, means in this example. So see 10 femtogram, so you are getting this much charge. 100 femtogram, you are getting this much charge. On 1 picogram, you are getting this much charge. So Now you can make a calibration curve for the PSA detection. For this biosensor, you can make the calibration curve. So here in the x-axis is the concentration, y-axis will be what? What will be the y-axis? Tell me, students, anyone? What will be the y-axis? Anyone, please? Guys, anyone? What will be the y-axis?
Potential, sir.
No, I am saying from this concentration chart, you are going to make a calibration curve, right? So this is for you got this chart from chronocoulometry. So x-axis you plot concentration. So what will be in the y-axis?
Charge.
Charge.
Right, charge. And what will be the unit? Millicoulomb, as I mentioned, right? So y-axis will be charge and concentration. So like zero concentration, you get this much charge, right? Then 10 femto you got this much, 100 femto you get this much, 1 pico you got this much. Then you can make a straight line, you get this one. Now, if I provide you some unknown sample, suppose this is your unknown sample, and you got just focus here in the right hand side, right? So suppose no, not here. Suppose you are using an unknown sample. So this is your unknown sample CC, right? So at the 200 second now you have to measure what is the charge amount. Okay. So how you measure? So this, then you have, if you make a straight line in the charge axis, so this one. So how much charge? Around, suppose it is 0.45 millicoulomb. Okay. So you are getting 0.45 millicoulomb from your unknown sample charge. So you already have the calibration chart in your hand. So that is y-axis. So from the y-axis, suppose this one 0.45. This charge. So now draw a straight line here and go to the concentration curve here. So it is, suppose it is around 95 picogram per ml. So your unknown sample content 95 picogram per ml. Your posted specific antigen. Clear?
Hello.
Yeah, tell me.
Sir, I was just thinking, what if we change the potential, the initial potential that we're applying through the potential stat? So if we change our potential, how will it affect these data?
Yeah, I think that I already told you last class. Let's repeat again. Here, right? I told you. So in the chronoamperometry, if you change the potential, what will happen? So suppose you are applying some very lower potential. So you are getting, so in the, this is the time and y-axis is the charge. Suppose you are applying 0.1 volt. So you will get this much, right? Then you are applying 0.3 volt. So you will get this much. Now you are applying 0.6 volt. You are getting this much. Now you are now applying like 0.7 volt. Then you are getting this much, right? So what will be the optimum then? So from here you have to make a histogram for optimization of potential. So from here you have to make the histogram that so in the histogram means you have means suppose 0.1 volt you are getting this much charge, then 0.3 volt you are getting 0.3 volt you are getting this much charge, then 0.6 volt you are getting here, and 0.7 volt, sorry, you are getting lower, 0.7 volt you are getting here. So which one will be your optimum applied potential? This is your 0.6, this is your 0.7. So then your optimum potential will be 0.6 because after 0.6 it is decreasing again, right? So like this way, you have to change the potential. You will get different charge. Then you have to fix one potential for your biosensor. Which potential you are going to apply? That optimization you have this optimization should be done before finalization any biosensor, or I mean that can be done by changing the different potential. So from here you got 0.6. So that one now you can That one now you can apply here. Yeah. Now got your point?
Yes, sir. Yes, sir.
Good. Hmm. Okay. So just a minute. Okay. So do you have any more questions, or can I start the new topic? Any more questions from you? No, right? Okay. So today I will teach you one more new topic, that is detection limit. Do you know detection limit? Anyone heard about this? I mean the term detection limit. Have you heard before?
Yes, sir.
Show more. Where
Sir, how?
where? Where?
Sir, I think if I have a concentration, say 1.25 some units, and if I have a concentration 1.24, will my biosensor be able to resolve uh, 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 these two concentrations very precisely? I think that is somewhat related to detection limit.
See that actually, say if their difference between two concentration is very low, then your biosensor should be very sensitive. Means that is called ultra sensitive biosensor. If you want to differentiate between the two concentration and their concentration difference is very low, like point level, then your biosensor should be very sensitive. That is called ultra sensitive biosensor. That I will teach you. Maybe not today, maybe next class I will teach you how we can develop a biosensor that can differentiate very low concentration difference. That is, or how we can develop a ultra sensitive biosensor. Okay, so more.
Yes, sir.
Okay.
Yes, sir.
Right. So do you know what the definition of limit of detection? Do you know?
Sir, I think I'm not sure, but till what level will my biosensor be able to detect a concentration?
Right.
Beyond a certain, for example, if we go down from 1 picometer or 1 nanogram to 1 picogram, then it won't be able to measure that. I think.
Right. The detection limit means that if you go below that limit, your sensor actually will be fail. Your sensor cannot detect. And if you go more than that limit, then only your sensor can detect all the concentration. So that point, that zone, that point is called detection limit zone or detection limit. So detection limit is a crucial factor to determine any kind of biosensor. So it can detect very smallest amount or very small concentration of analyte that present in your sample. So in one word, I can say the smallest concentration can be detected by your biosensor. Clear? The smallest concentration, I mean the lowest concentration. The lowest concentration that can be detected, that is your detection limit. So how we can predict, how we can calculate the detection limit, right? That is now question. So how we can calculate the detection limit? See. So for the calculation of the detection limit, calibration plot should be in your hand. Calibration plot. So first criteria, you have to plot the calibration curve first. So suppose this is your concentration in x-axis, y-axis is the charge. So it means from cc, chronocoulometry you are using, right? Charge means milli-coulomb, concentration suppose nanogram per ml. So all the concentration here nanogram per ml. So 0 case here, then 1 nano, 10 nano, 100 nano, 1 micro, 10 micro, something like this way. So you are increasing the concentration. So this is your calibration curve, right? This should be in your hand. Now, in your biosensor, you have to run one concentration 3 times. Why we need to run? So So you have to check the reproducibility. So now one term coming, that is the reproducibility. Right? Reproducibility means if you run the same sensor in the same concentration, when you run one like just today morning, you run the sensor. You suppose you got 3 millicoulomb, but in the afternoon when you run your biosensor with the same concentration, but you are getting 100 millicoulomb. Is it reproducible? Guys, so morning 3, afternoon you are getting 100 millicoulomb. Is it
No,
reproducible?
sir. No,
It is
sir.
not.
No, sir.
But if you get 3.05 millicoulomb, is it reproducible?
Yes, sir.
Yes, sir.
But
Yes.
Little variation there, right?
yeah.
But that is acceptable actually. So that's why you have to put the error bar here. Error bar means in the concentration you will get something like this. Means morning you got here, at the afternoon maybe you got here, maybe at the night you got here, something like this. So you have to run at least 3 times in each concentration. In each concentration same, sensor same, everything same, just you are running different time or at the same time many times you are running. So this is the error bar. Means error bar means if you get the charge within this region, actually it is corresponds to your zero concentration. Similar way here, if you run your biosensor and if you get the charge within this region, this is kind of the region, not one point. So if you get within this region, so this is corresponds to within this concentration. Something like this. So you'll get some error bar. So that's why sometimes when you run some unknown sample, that time also you have to run 3 times or 4 times. Then also you will get similar type this region. Then you can say your concentration, actually whatever we are getting 4.05 suppose nanogram per ml you are getting from your unknown sample. I mean, is it exactly that much? It can be 4.1 or maybe 4.2, so something like this. So but it should be nearby 4 up and down. So if you get too much variation, then your sensor is not reproducible. Okay, so that's why it is recommended you should run your sensor at least 3 times. Okay, so something like this error bar you will get. So this is a complete now concentration calibration curve. Now for determination of detection limit, we are focusing the zero data first. So this is your zero data. So you have to run at least 3 times, as I said. So this is your, then you have to put a straight line like this in the concentration, the parallel straight line you have to draw. So this is your zero concentration data line. Okay. Now, so this is your zero concentration data line, and this charge corresponds to 0. Now, to get the detection limit, you have to multiply with 3 with this. So see why I am putting, so it can be from here also, it can be from here also, but we are taking that point from the middle, that point, I mean from the error bar, from the center you have to plot. So this is called a standard deviation. We'll get a standard deviation from each point. Standard deviation, that we are saying SD. I think you learn already mathematics in the 10+2 up to 10+2. You know what is the standard deviation, right? Standard deviation is this kind of things. So you have to get the standard deviation how much. So this point is actually your zero concentration data. This center point. This is the standard deviation of your zero concentration, and this center point you have to collect the charge from the y-axis. So this is the standard deviation of your standard deviation point you will get from your zero data. Now you have to multiply with 3 standard deviation of the zero data. So if it is like suppose it is 0.1 volt, 0.1 millicoulomb, then if you multiply with 3, then it will be here 0.3, right? If it is 0.1, millicoulomb, then it will be 0.3 millicoulomb. So this is the 3 into 0 standard deviation data. So this line actually erode your threshold line. This line is called your detection limit line. Means if you go below this line, that will not be considered your detection by your biosensor. You have to measure the concentration above this line. Now the question, why we multiply 3 with this 0? See, generally, see 0 is our reference, our very standard data. Why we are going up, then 0, 3 times up? Why? Suppose I develop a biosensor for this prostate specific antigen using same protocol, same thing. Now Suman developed one biosensor using same protocol, same thing. But when we measure the biosensor for Mai and Suman, is the data whatever we'll get is it exactly same or not? It will be exactly same or not? The the output data will be exactly same or no?
No, sir, it will not be the same.
It will not be same. So it will depend on hand to hand, man to man. It will vary, right? Whatever you develop a biosensor in your lab, but I will develop one biosensor in my lab. Although same protocol, same biosensor, it will not be exactly same. So that's why, although you are saying this is the 0 data, but because your biosensor not only you will use, other people also use your biosensor, right? So when the same biosensor, if I run the biosensor, maybe I will get some data. If someone go, if Bihuti use something, they will go, they will get some different data. That's why to minimize the user error, to minimize this user error, we are multiplying with 3. That we decided, international actually we decided that 3 multiply will be the standard. So we decided that 3, if we multiply this, it will go somehow above, right? Then 0. So these above data actually will consider at the detection limit, not the 0 data will consider. To minimize the user handling, that error. So now your actual 0 bar will be this one. This 3 into SD. This one will be your 0 data. But you see, your 1 nanogram per ml, that bar, see, it coincide with your 3 standard time 0 data, right? Right, guys? Your 1 nanogram per ml concentration, it is overlap with your 3 standard deviation 0 line. Right?
Sir, one doubt, sir.
Huh.
So standard deviation of the whole data or the first one data?
No,
which one, sir?
Standard deviation of the 0 data, 0.
Okay, that 3 triplicate will take that standard deviation, right, sir?
That data, So I'm telling about 0, 1.
Okay, sir.
Okay.
Okay.
So you see that one is now merged, or now you can say the what do you say, the overlap, that 1 nanogram per ml standard deviation data, you can see is the overlap, right? This 3 times standard deviation of 0 data, right or not?
It
Guys?
looks like that. It looks like that, sir.
Looks like, right? Yeah. So then what will be your detection limit? Your detection limit will be the 1 nanogram per ml, not this one. Actual 0 data, not this one. So your detection limit will be this one, we will consider for this biosensor. Clear? So what? So how we will calculate the detection limit? So we have to multiply with 3 with the standard deviation of the 0. Then whatever we will get, that current will be considered that current will help you to determine your lowest concentration data. That can be predicted from your biosensor. Okay, so I will show you some example here. You can see. So here see like different cyclic voltammetry, like 0, this is the 100 femtogram, this is 1 picogram, then 10 picogram. Then suppose so here actually we fixed one here. You can see this potential. So this is cyclic voltammetry. So we have to fix a potential like this one, like 0.01 volt, something like this. So in this potential, we just got all the current. So right hand side you can see we plot like current microamps versus concentration of troponin I. This is for the troponin I. Troponin I, one kind of the cardio biomarker, I mean heart disease related biomarker. So see, we plot here all the case. So it is not exactly straight line. So something like this we got. So now we can see your zero data maybe corresponds to here, but your 3 times standard deviation data is a little bit off. So it is your actually detection limit, and it is actually merged with your 100 femtogram per ml. So your detection limit, that's why 100 femtogram per ml, not less than this. Although you can go less than maybe 100 femto, but as 3 times standard deviation line is here, so it will be considered your detection limit zone. Clear, guys?
Sir, here 3 standard deviation is not intersecting with anyone, sir. How will detect the concentration?
3 times standard deviation not intersect with
the point which you mentioned earlier, the first point or second point. How you will detect the concentration?
Maybe some concentration here not plotted. So okay, let's I will plot one manually. Just wait. Okay, I will show you this one. Yeah, sometime there is some cases. Let's plot. So what you have to do, you have to plot some calibration first, right? Here concentration, and here what we plot here, current, right? Current. So like so this is your 3 standard deviation. Suppose suppose here, so you can say here, so maybe this one data, suppose this one 1 picogram per ml. Suppose here one data, this is 10 picogram per ml. Suppose here 100 picogram per ml, and this is 1 nanogram per ml. Okay, so now what you have to do, you have to draw a straight line within few concentration. You have to draw a straight line. So this intersect will be your, so this is 1 pico, this is 1 pico, this is 10 pico. Suppose this one 3 pico, 3 picogram per ml. So 3 picogram per ml your detection limit. Clear?
Yes, sir.
So like this way, we can calculate the detection limit. See, why actually you got 1 picogram per ml data because your sensor can detect. That's why you got. But as it is lower than 3 standard deviation, so it is not your detection limit. So your detection limit will be that that one that can intersect with your concentration card. So this one intersect, suppose 3 picogram, right? So this is your detection limit. Guys, please ask me right now if you not clear. I know many times that students are asking during the exam time, they are asking, sir, it is not clear to me, that's why I not writing well this detection limit definition and calculation, because I will give you some problem during the exam and you have to calculate detection limit. So please ask me now, I will clarify you.
Sir, this thing is not clear. Means standard deviation of what? Is my first question. Standard deviation of the entire entire current versus concentration data, or standard deviation of the current concentration data at my zero measurement?
Standard deviation of only each concentration. So when you are considering zero, so you have to get the standard deviation only zero case. So it's like you measure three data, right, for zero. So you got one, suppose 5 milliampere, 5.01 or 5.2 milliampere, like this. So you have to collect the standard deviation of these 3 data. Okay, first point clear.
Okay. Yes.
Then second.
So we have to multiply this with 3 to get this line beyond which we cannot measure.
Right. You have to multiply 3 by using this standard deviation data.
Okay.
Yeah. So 3 times standard deviation data. You have to multiply with 3 with standard deviation of 0. Standard deviation of 0. So this is for 0, not for other concentration. But now, when you got this curve, you got already this dot line. This is called your detection limit. This will help you detection limit. Then you have to plot the other concentration also again here, not the 0, other one, the other one. So you can get the standard deviation here also, the standard deviation. Then you can plot the other concentration, and then you can make a straight line, and this straight line will intersect with your 3 times standard deviation value. This intersect on will be your detection limit. Clear?
Sir, I am not getting the second one, sir.
Which
So,
one?
the standard deviation of the 0 should be multiplied with 3, or any concentrations we can multiply with 3. It should be always the first 0 concentration.
Yes, you're right. We had with the 0, not any other. As I saying, you at first you have to collect the current for 0, then other concentration too. Okay. Then you plot the calibration curve, right? 0 and other concentration also. Now, when you determine the detection limit, that time you have to consider only 0, not other concentration, only 0. Then collect the standard deviation value from the 0, multiply with 3 with 0 standard deviation, then put that dot straight line. So that straight line will help you now to determine the detection limit concentration. As I showed you here, okay, I removed it. I showed you maybe one concentration here, another concentration here. So see, suppose this is 1 picogram per ml, right? This data you got, and but your 3 times standard deviation actually here, right? So but you got actually 1 picogram per ml this current from your biosensor, but it is below this line, uh, 3 times standard deviation of 0 line. So it is not your detection limit. Your detection limit will be above this. Clear? Vibhuti, clear? Sumon?
Yes, sir.
Sumon, is it clear?
Yes, sir.
Akash Sharma, how are you, Akash?
Yes, sir.
Is it fine?
Yes, sir.
Yeah. So in the exam, actually, let's take few more class. Then I will give you some tutorial. That time we will discuss some problems, some question answer type discussion. That similar type question will come in the exam also. So we'll discuss maybe. Let's take one more class. Then I will take a tutorial.
Sir, will you give example problems like once can you solve an example, just an example and show before giving the tutorials?
Do you want some example today? You want to show you, or you are asking me before the tutorial?
No, before the tutorial, just
Sure,
maybe
sure.
not today, but somewhere.
Sure. I will give you. Sure.
Thank you, sir.
Adesh Khanna. What is your name? Adesh, right?
Adish. Yes, sir.
Good. Aman? Hi, Aman. How are you?
Sir, I'm good.
Okay. So is it okay? Fine. This detection limit calculation, everything. And is it?
Yes, sir, I'm.
Okay. So please. So please read also this one. Then I will ask you. Brotin, are you there?
Yes, sir.
Is it clear how to detect the like prostate specific antigen using this very simple that gold conjugated secondary antibody coated biosensor and detection limit for calculation? Very simple, right?
Yes, sir.
Okay, good. So this kind of sensor we will develop, and finally we will develop some device. So just maybe until maybe I will take few more classes. I will teach you all the basic stuff for biosensor. Then I will go to the device. then bring everything to the sensor surface to a device. That I will teach you.
Yes, sir. Sure, sir.
Okay. Any other things? Harshit Chaudhary.
Yes, sir.
So is it everything fine, right?
Yes, sir. Yes, sir.
Okay, but please keep asking the question because we this is almost 2-hour class, so sometimes